So welcome back, everyone. And we have finally reached the final lecture of this course. And this will be the lecture where we're going to introduce the last tool that is required for you to be able to solve the final applicative exercise. You will be tutored by Dr. Pedrielli in the very last 12 hours of the course. As you will see, in those lectures, you will be, he will review for you the theoretical setup of what is called the Hartree-Fock method for quantum many-body problems. And then you will, download code that implements that method and use it to evaluate the electronic structure of simple molecules. And then do some exercise in order to appreciate and discuss the results of your calculation. So what I will be doing today is to introduce to you in a very superficial way the concepts, or at least the idea that are behind the Hartree-Fock method. So once again, let's frame things into the proper context. What we are actually interested in is the electronic structure problem, or more simply, the electronic problem of quantum chemistry. And what the electronic problem is actually aiming at providing are two main outcomes. Well, the energy as a function of the collection of static nuclear coordinates. So you put the nuclei in static positions. And then you solve the Schrödinger equation for static nuclear positions. Once you have this energy, we discussed that, for instance, you may take the gradient and obtain the force that is acting on each of these nuclei, if you want to treat them as classical particles. As a result, the emergent force that arises as a result of the electronic structure. So this is the key ingredient for performing molecular mechanics simulations, in which you discuss the mechanics of a macromolecule in a classical setup, where each nuclei is actually experiencing different forces, and therefore the system evolves according to, say, Hamilton's dynamics. The second ingredient that we might be interested in getting from this kind of calculation is the wave functions for the electrons, or of course an approximate wave function for the electron, given the collection of fixed nuclear coordinates as a parameter. So once again, these labels X and Q are macro labels. And to be very specific, Q is the collection of nuclear coordinates. In other words, the collection of coordinates of all the nuclearies, atomic nuclei in my molecule. And X is a collection of electron and spin, or better to say, Z component of the spin. Because as you know, once you go from, say, boson to fermions, the spin does not only play, say, an accessory role, describing, for instance, the interaction of the particles with external magnetic fields, but it plays a central role because it actually interferes in a heavy way on the structure of the wave function because of the Pauli exclusion principle. Therefore, when you talk about the structure of the electronic wave functions, you do have to take into account of the presence of spin. Now, according to the discussion we've had in the last several days, I think it is clear for everyone that indeed you need to make approximations if you want to access this information. The solution of a quantum many-body problem in exact form is in fact completely impossible. So how do we perform such a what are the correct approximations? I mean, there is a full industry of methods that have been developed over the decades in quantum chemistry that enable people to access calculations at the different degrees of approximations. Some of these methods are good for a first, first quick and dirty answer. Other are sort of optimal compromises between computational costs and accuracy, so that they're used in a wider variety of physical systems. And finally, some methods are extremely expensive, therefore applicable only to small systems. However, they're supposed to be very accurate. Which one should you use depends very much on what is the problem you're looking at and how accurate theoretical information you need, for example, to compare with experiments. Clearly, if the experiments have huge error bars, then of course, you need very, very accurate theoretical predictions. And a key word that you hear very often in this field is that of chemical accuracy. You need to achieve chemical accuracy. Chemical accuracy, at least for a physicist's point of view, means a whole lot of accuracy. You should be realizing that in many fields of theoretical physics, people are content with semi-qualitative predictions. Let me give an example. Suppose you want to compute from very first principle the mass of a proton. You might not be aware of the fact that the mass of the proton is a composite object and it has an internal structure, and that you can compute the mass of the proton based on more fundamental physics. This is a business for nuclear, subnuclear, high-energy physicists. That will never be of any of your concern if you stay in computational biology. However, what people typically are after in that case are the general mechanisms that are responsible for the qualitative organization of the masses of the different subatomic particles. And as long as you get some kind of a precision, which is in the order of 10%, I think it's a reasonable calculation. A, because they're very difficult calculation. In that case, you need to take into account the relativistic quantum mechanical effects, which put the scale of complexity to a whole different scale. But also because if you really needed much better information, all these masses, mass of all subatomic particles, are available from experiments. So, you got a general understanding of their structure, of the spectrum with the different masses from theory, but you can measure all of them. So the moments that you really need an accurate calculation to know the value, you don't use calculations. You typically take the experimental value. Now in chemistry, things are a little bit different, because when experiments are available, they are generally extremely accurate, and therefore enable you to get a very, very detailed testing of the model. On the other hand, the phenomenology of condensed matter in general and in chemistry in particular is virtually infinite. The number of nuclei, atomic nuclei, is in the few hundred, right? Take the heaviest element. I think it's somewhere after you pass the uranium. I don't even know it, but it's going to be in a few hundred of particles. So there are a few hundred nuclei you can worry about. You can think about some of them can be isotopes. Say 500 different physical systems, and you're done. Clearly, there are more than 500 molecules in nature, orders of magnitude. So in most cases, you don't have experimental information, very detailed available, or information that can be provided by experiment is only limited to a certain global macroscopic observables. However, in other cases, you have very detailed information. So, and the second important feature that distinguishes chemistry, if you want, from the rest of physics, and I really don't think there should be a distinction between theoretical chemistry and physics from the fundamental point of view, but typically it's a different approach because in chemistry, especially in biochemistry, you need accuracy for the whole field to be useful at all. You see, if I get the mass of the proton wrong by 10%, probably most of the implications of that calculation are going to hold on anyway. However, if my temperature, which is changes by 10% in absolute values, so that would be 30 degrees up, because 300 Kelvin plus 30 Kelvin. Well, that means that all my proteins in my body are going to denaturate, most of them, and I'm going to die. Simply. So you see, a few percent, and temperature is a measure of the available energy. So if I miss all my energy by 10%, it means that all my thermodynamics is going to be completely wrong. And so all the consideration I can do about macromolecules and thermodynamic conditions are be completely spoiled by the very tiny error. So it is very important that each energy for each relevant degrees of freedom being locked, for instance, by an interaction, that should be below the typical thermal energy for 1 degree of freedom, which is of the order of say, a couple of kilojoules per mole. So this is a huge, huge, huge challenge. And this is, in a wordy way, what we mean by chemical accuracy in the field of molecular simulations. And is, in fact, a challenge in the field. So can we reach chemical accuracy? Well, in some cases we can, and mostly this is due by the introduction of a very powerful method called density functional theory. But we will not discuss density functional theory in the further exercise, although one in principle could, but I find it that, density functional theory belongs to one extra layer of complication than the one that we're going to discuss. And it will take me, say, another 10 hours to bring you there in a decent, so to say, level of theoretical equivalence. I find it more didactic and inspiring to stick to a method called Hartree-Fock, which is the first quick and dirty calculation you can perform. Because if you can understand Hartree-Fock, then, if you want to go into a thesis that goes into scientific work that really heavily relies on quantum chemical calculation, then you are all equipped to read the literature on density functional theory and move on. But if you do not need to do that, well, with density function, with the Hartree-Fock calculation, you already have enough experience of what it means to evaluate this, to tackle an electronic problem. And you let other people worry about providing you with the correct answer. In fact, Hartree-Fock plays a pivotal role in quantum chemistry calculation to the point that sometimes you hear this keyword post-Hartree-Fock to denote that there are Hartree-Fock calculations, quick and dirty calculation, and post-Hartree-Fock that are supposed to aiming at accuracy. Now, anytime you make statements like this, you sort of are exposing yourself to criticisms, and rightfully so, because there are situations in which this like black and white distinction really do not hold, and that sometimes there are subfield dependence. In some fields, quick and dirty means something different than in a very, very closely related subfield. So they should be taken with a grain of salt. But this is just to say more or less where we stand in the level of complicacy of the quantum anybody problem for the electronic structure. So having said all this long premise, let me describe to you what is Hartree-Fock method. So basically, the Hartree-Fock method is the idea of merging two key approximations we have already discussed in this course and putting them together. So what Hartree-Fock, and let me spell it out for you, actually means is the joining of the following two approximations. Mean field for electrons and variation. If you want, Ritz variational approximation. So how do we combine these two very, very common and fruitful ideas in theoretical physics and theoretical chemistry into a single approach? Well, let's see. The mean field approximation means, in the end, that I can impose that a wave function can be factorized as products of independent particle wave functions, or linear combinations of products that satisfy Pauli principle, or even better stated, that the wave function for my electrons is a Slater determinant. I will go back to this in a moment. If you are confused here, I recommend you stop this lecture, go back on the lecture where I introduced the mean field approximation and the Slater determinants, and rewind it and watch it again. And you will discover, you will be reminded of all the arguments we made that led us ultimately to define the wave functions as Slater determinant. Now, the Slater determinant simply tells, the mean field approximation simply tells you how to relate a complex many-body wave function, which contains all correlations, to n different one-body wave function that can be solved independently. It is much simpler, exponentially simpler, to solve n one-body Schrödinger equation than it is to solve one n-body Schrödinger equation. And you can actually argue that there's an exponential scaling between these two calculations. So clearly, the mean field approximation really brings down exponentially the computational load of solving the electronic problem. But clearly, one is left with the question, what is the best possible single particle wave function I can get in a Schrödinger problem? And to answer that, one relies on the Ritz variation case. Okay. So the way we're going to do that, now I will not go through the derivation of the Hartree-Fock in this course. I mean, I used to do it at some point, and I was realizing that it wasn't very informative because that actually resulted in having students breaking their minds on some rather intricate derivation for somebody in his own first course in quantum mechanics. And if you invest all of that time in trying to digest that derivation, you don't have time left to understand the basics of quantum mechanics. So I think it's better not to do that. Now, let me remind you the ingredients of these calculations. Remember, when you're dealing with a many-body wave function, you are dealing with essentially positions in spin. And you can do that in different ways. One way is to, if you have for boson, what for boson is suppose you have a particle and it's a boson particle. When you go to fermion, you basically upgrade the particle to a pairs of wave function, each one related to the probability of observing the particle with a given spin at a given position. There is an alternative way which you use that are equivalent from the conceptual point of view at some point. One, you can go from one to the other. That consisted to factorize all the spin degrees of freedom in the spin wave function and all the spatial degrees of freedom in the spatial wave function. And it is, while this is possible in some cases, it's not very practical in very complicated problems. So this is certainly the most general way to do that. But if you want, you can generalize this to say, well, I have different wave functions at positions. Why? Because, if you have a new field, this could be phi ground state down or phi ground state up, and this would be I equal 1 or I equal 2. These are in principle two wave functions. If you put a particle in the first excited state or a P wave, depending on the detail of your problem, this could be an S wave, it could be a second S wave, and this could be like phi 1 down, and this could be another function, phi 2 up, and so on and so forth. So you have a multitude of states you could place an electron in general, and we can label that with an index I here, which does include spin as well. So in a later determinal sort of formalism, and this is very general, we're going to write the money-body wave function as the following determinant. We already discussed that. Now, once the mathematics describing how to place this wave function within the context of variational principles, that corresponds of writing a functional that describes a function of these functions. It's called a functional, and it's a function of, the expectation energy, value of the energy depends on the choice of this function, right? And that's what you want to make minimum. And this will produce a condition on this function, as always. Now, this is what is called a functional formalism, and let me not go into that, like I said before. But once you do that, you arrive to a set of coupled Schrödinger equations for a single particle. And let me just write those equations as if they were God-given or whatever entity given. Now you get following expression. I'm setting, for simplicity, E to 1. I should use the E. To use X. I was using the X label here. Let me first write, and then I will comment on this. Okay, so it looks horrible. And to some extent, it is horrible. But let's try to digest what it means. You'll find all this in the notes that are available in my webpage. First of all, what we got here? We got an equation for the orbital of the lambda electron. That is, you have n electrons, and in principle, you have n different wave functions for each of them, because they could be in all different states. Remember, this. And if some of them are P states, you have 6. If they're S states, you have 2. So you have, in general, n different wave functions for all the electrons. But since the electrons are indistinguishable, of course, any electron can be in any wave function. But you have n different wave functions. And so what this lambda means, phi lambda is what you want to compute, and lambda is the index and I need 2 indices because I have different wave functions. In particular, lambda goes from 1 to n if I have n electrons. Remember, I cannot have two electrons in the same wave function because of Pauli principle. So if I have n electrons, I must have n wave functions. And I label my electrons with an index I. Let me go around. Putting the index in blue to remind myself, let's say xi. To remind myself that this is the distance from the nucleus, for the distance from the nucleus. Well, this is, okay, fine. This is, okay, so let's be a little bit more precise. Here is a collection of Coulomb attraction with respect to all the atoms. And what this is actually the Coulomb attraction with respect to the alpha nucleus, which I will call Q alpha minus Xi. Right, so what this is actually saying is that this is the Coulomb attraction of the ith electron with respect to the alpha nucleus. Remember the lecture of the concept of sharing the electron between different nuclei. So let me replace everywhere I see lambda with this color because it tells me which wave function I'm actually trying to compute. The lambda of these orbitals here. So let me draw here, for instance, here, one of these points will be in this watery color, just to remind you that I'm interested in computing one of those orbitals. So here comes the orbital, here comes the orbitals. Okay, so here comes the position of the ith electron, because any of the ith n electrons can stand in this state. So there are n electrons, x1, xn, and all of them can be found in this state because I have to take all possible combinations of electrons in all possible wave function described with Slater determinant. So again, here comes xi. Here comes xi. So now I guess we understand what lambda stands for and what xi stands for. And these derivatives here are with respect to xi, so I'm not going to use the same color. But as you can see in this formula, so we understand what this formula is to compute. It computes the lambda orbital and as a function of the ith electron. Very good. Now, there are additional terms here. Now, so let's take a look at this quantity here. What is this quantity? This, if you look at it, this is the average, is the probability of finding any of the electrons at position xj, integrated over xj. So basically what this combination here is telling me is the probability of all electrons in the system at point xj. And what this is doing is computing the Coulomb repulsion between the electron at xi and a charge density provided by all electrons in xj integrating over all xj. So in other words, is the electron to charge density interaction. So I could replace this by saying that there's a charge density at some point j provided by all electrons in the system. So let me draw it here with this stupid cartoon. Here are my atomic nuclei. I have a charge density, which I will draw maybe with this. Some point is going to be heavier. Some point is going to be lighter. This is my charge density. That is this quantity here. And when I compute the interaction of my lambda electron, eth electron, sorry, I'm going to write here. I'm computing the Coulomb interaction between this electron, which is the eth electron, and this charge density. You see? This is the Coulomb interaction because this is the Coulomb field, not with a point charge. If this charge density were just a point charge at J, this would be the Coulomb potential that appears in the standard Schrödinger equation. So if I take away all other electrons, I put just one electron, this will become typical, this charge density will be charge density of the other electron, and this will be the charge repulsion between the electron in xj and the electron in xi. But in a mean field approach, what I do, remember, is compute the interaction of a particle with all other particles in the system. So this is the charge density provided by all other particles. So if I momentarily close my eyes to this mysterious second term here, which I will need to comment upon in a moment, the Schrödinger equation for a single particle, called the Hartree equation, would be quite meaningful, because it means that you want to know the wave function of one of the particles in the system in mean field approximation. You have to solve a Schrödinger equation in which you take into account of the kinetic energy of this particle, the interaction with the static nucleus as a potential energy, it's being there, and the interaction with the average charge density produced by all other particles in the system. And of course, this electron density depends on the single particle wave function of all other electrons. So this will have to be computed, and it's not given externally in the calculation, but internally. What do I mean? This is an essential point of Hartree-Fock. So listen up very carefully. I want to emphasize the difference between this and this term. And momentarily, let's not worry about this term. Pretend for a moment this term is not even there. And you know what? Let's for a moment even erase it for sake of clarity. We'll put it back there in a moment. So if we erase it for sake of clarity, this becomes what is known as the Hartree equation. What this equation says? It says, I have single particle wave function. You can see there's only one derivative here. My single particle wave function is this phi lambda, which is the object of my calculation. So I'm going to use this. I really want to find this phi lambda. But in order to find this phi lambda, I need to solve a single particle Schrödinger equation, which depends on the charge produced by all electrons in the system. And this charge is itself a sum of single particle densities. Because, you know, what is the charge density? Is the probability of having an electron in a given point, right? So it appears that to solve for the equation of phi lambda, I need to know all other wave functions of all the other electrons in the system. So it looks like it's an unsolvable problem, because to solve for phi lambda, I need to know all, see the sum, all of the phi mu. And then use this information that I'm looking for as an input for an equation that gives me all of the phi lambdas if I vary lambda from 1 to n. This is called a self-consistent equation. Self-consistent means I need the answer to formulate the problem. I need the orbitals to write down the charge density that I need to write down a Schrödinger equation that gives me the orbital. Rewind, at this point, go back and rewind the lecture based on this sentence that I think you will be clarified. I need the orbitals, the phi mu, these are the orbitals of phi lambda. I need them all to be able to write down the density that enters in the equation that I need to solve to find those orbitals. So I need them in input in the equation, and the output of the equation are the same thing. So how can I write an equation where the input and the output are both together? And the answer is through an iterative procedure. What is an iterative procedure? You start with a reasonable guess of your wave function. You assume this guess to compute a reasonable estimate of this charge by simply taking this product. At this point, your equation becomes an equation for phi lambda only because this is fixed. The rho is already fixed from your guess. And you solve this equation, you get phi. Once you get phi, you go back and get a better estimate for this rho, because now you can use a better estimate than your initial guess. You have computed the rho. And now your equation has changed because there's a different rho, and if you solve this equation, you get a better estimate for phi. So in other words, what you get is a recursive algorithm. And you start from guess, phi, compute, rho, compute phi, and then go back. Sorry, not back to guess phi. Go back to compute rho. And you go in a circle here, computing rho from phi, and then using this information to obtain phi, and then go back and using to recompute rho and recompute phi until the result doesn't change anymore. We call convergence when this new phi that you obtain, a new rho, stop depending on the number of iterations. And that's where you stop. So this equation that looked terrible, the Hartree equation, is actually quite meaningful now. In a mean field, you want to compute the charge density produced by other electrons and solve the Schrödinger equation of the particle in a field produced by all the electrons. And the way you do it is simply by assuming some reasonable guess of your charge density, computing the wave function in the charge density, excuse me, refining your initial estimate of the charge density, and recomputing the Schrödinger equation. Each of these Schrödinger equations will be a hard Schrödinger equation to solve, even if it's a one-body problem. It's a Schrödinger equation in a complex external electrostatic field. So in principle, you might have to use variational approximations to solve these equations as well, or other sort of approximation. And I leave to Andrea Pedrielli's lectures to give you a little bit of details on how you do that. But at least from a conceptual level, this is what is an iterative, Hartree self-consistent approach is. Okay, so let me go back here and restore the summation over the position, the density at xj, but now let me tackle the problem that in the equation that I described before. So before I go into that, here is where now my wave function enters. And I'm using a different index here because this summation is on a different particle, right? Okay. Now, let me go back to the fact that in the equation that I wrote before, there was another term. Still, the sum was over mu. So we understand this has to do with something that concerns all the other all the electrons in general, that collectively describe the effect of all the electrons in the system interacting with my particle. But now the combinations of wave function is more puzzling. I'm going to use the purple for mu index. And I'm going to keep on using x, j, phi, lambda, xi. And I'm going to use the red character for the phi. Okay. So I think it's quite convenient to do the following. I'm just, you're going to leave it as it is in your notes, but I found it more understandable if you switch the order. And therefore, even here, I'm going to put integral in dxj and the summation of the mu inside. You can always swap the order of integrals and sum, of course. And then I'm going to have 1 over xj negative x xi or xj doesn't really make any difference because they are in, this is the same xi minus xj for obvious reasons. And then I have phi, and again, here I have my, but now I have my mu here of xi. Okay, so this term is mysterious because you see it involves a combination that is not a density. The wave function appears in a way that is not simply physically interpretable. It is very difficult to interpret what this term is. And in fact, there's no classical interpretation. The reason is that our interpretation, as our physical intuition of what this term means, come from our classical analogies, right? Same, but sometimes when we're dealing with the electrons, we stumbled into something that has no classical analogy. So for instance, when we were dealing with spin, we immediately began to mumble, yes, the spin, the electrons are, the spin of the electron is basically something to do with the rotation of the electron about its own axis. But then we immediately understand this was not the case because the quanta of this angular momentum were different and the particles were point-like. So how can you have a finite current if the particle is point-like? So clearly we had to give up this classical intuition. Likewise, there's no classical intuition for Pauli exclusion principle, because you can pretty much, work as hard as you can, but you'll never be able to find any classical system obeying Pauli symmetry and Pauli exclusion exclusion principle. Now, when you impose Pauli symmetry, Fermi symmetry, by using a later determinant rather than the simple product of wave function, you generate the second term. So this term here comes from the fact that you have used as later determinant that mixes up wave functions in a non-trivial way to ensure the Pauli principle. As a result, you get a contribution to the potential energy that still involves your self-consistent estimate of the wave functions, but has no classical interpretation. And this term is called the exchange term. It is still an energy, a potential energy if you want. It's still obtained from your previous estimates of the wave function, but it has no classical counterpart. From the practical point of view, however, this is not a big deal, because all you have to do is to take into account, but it doesn't change the general iterative procedure, because still, you start from a guess, even in this Hartree equation with exchange term, which is called Hartree-Fock. Fock was responsible for introducing this exchange term that comes from taking into account of this later determinant structure rather than simple product structure for fermions. Now, if you use the exchange term, the equation is more involved, but the procedure to solve it is still the same. You guess phi's, all the orbitals, compute rho and the exchange term. This is the exchange term, this is rho. But in this case, you compute rho. In this case, you compute the entire system, because you put one of the guess wave function here, and the other one you put it here. But still, you get an equation for phi lambda, you see? So you actually solve for phi lambda. So the correct statement would be you guess the phi mu's. You use this information for solve for phi lambdas. And then you improve on your phi mu's and you solve for lambda, and blah, 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 until you've reached convergence. Now, you will be downloading the code that does this for you. You will not have to code yourself a program that does that. That would be too much to ask for computational biologists. But the code that you will be dealing with Andrea will do exactly this. And so I hope this lecture was at least some very basic introductory lecture to explain to you what you will be doing from the fundamental point of view of quantum mechanics. But in the end, this will be in your background, and you will be able to compute electronic structures and energies and optimize the structure of small molecules. So let me just say that you will be asked to present PowerPoint presentation with all the results of the exercise that I will guide you through. I don't need you to have a stellar presentation. I don't need you to have any written report. I need an organized set of panels in which you have all the figures with all the information required to explain to me what you found, so that I can ask you, what is this plot? What does it mean? How did you obtain it? So don't spend much on the aesthetics. Don't spend much time on the aesthetics. Don't spend much time in having a super smart and elegant presentation. I'm not going to value that too much. But don't present to me like a messy collection of plots, like 5 plots in a single panel, where we're going to spend a long time in trying to dig out the information. Yet, give me all the curves and values that you're going to try, put it there, so that I can see that you've done it, and I can ask you a few questions on how you did it. And then we'll continue the exam, the oral examinations on the theory that we discussed. So that's it. We will still meet maybe a couple of times in January if you need, for questions and answers. And thank you for taking this course. It was a difficult year for you, I guess, and for me, I should say, because teaching a course that is not the easiest for people who don't have a background, a bachelor in physics, by remote. Um, like I said in my live lectures, it's challenging. I don't say that to apologize. I mean, I think it's every teacher's duty to do as good as possible. Nonetheless, I think it was a challenge. I hope some of the messages has passed, and you're welcome to ask me questions anytime. Contact me for going through questions in the break before the exams. Until then, good luck with your studies and with your further career. Bye-bye.